Number 1 from section 4.1. This section has got a lot of important stuff in it, even though the problems are actually pretty easy. But let's take a look at number 1. It says, let V be the set of vectors shown below. So it sounds like it's the set of 2x1 vectors, but the x-coordinate's got to be positive, the y-coordinate's got to be negative. Okay, so part A says, if U and V are in V, is U plus V in V. So U and V are in V, but is U plus V in V? That's the question. Okay, well, I don't know. Let's see. We could let x1, y1 be in V, and we could also let x2, y2 be in V. So the sum is this. Okay, so essentially the x's are both positive, and when you add two positive numbers, it's still positive. When you add two negative numbers, it's still negative. So it sounds like it is in V. Yes, it's closed under addition. Part B. Find a specific vector u in V and a specific scalar c such that cu is not in V. So that would prove it's not a vector space. But they're basically saying find a u in V and a real number c such that cu is not in V. Okay? If we can find such a u and such a c, that'll prove that's not a vector space because both of those conditions have to be satisfied. It also has to have the zero vector, by the way. Okay. So I think that'll be pretty easy because I think if you just choose c to be -1, that'll probably do it. So how about if we do this? I'm going to let u be 1, -1. And that's certainly in V, isn't it? Because the x has got to be positive, the y's got to be negative. But if we choose c to be -1, then c times u is -1 times this vector, and that is -1, 1. But that's not in V, is it? Because by definition, the first one's got to be positive, the second one's got to be negative. So that proves it's not a vector space. So kind of easy stuff, but it involves some definitions of a vector space. So a vector space has got to be closed under addition and scalar multiplication, and it's got to contain the zero vector.